Alright, so let's start trig. So all of trig is based on the notion of a right triangle. So this here, I've drawn a right triangle. Recall that right triangle is a triangle that has, one angle that is 90 degrees. And then of course it'll have two other angles. So let's label this angle here, theta. Okay. And of course we know that the sum of the degrees in a triangle have to sum up to 180 degrees. So that means since we know this angle and we know this angle is completely determined by 180 minus theta minus 90 degrees. So we know exactly what this angle is. That means that all the angles in this triangle are fully determined, in this right triangle are fully determined by providing this angle theta. And we already know the other angle has to be 90 degrees because it's right. Okay? So that means that a triangle is fully determined up to similarity by just giving this angle theta. And what do I mean by that? It means that, if I have another triangle that's also a right triangle that has this angle theta here, and it has different length, let's call it x and y, and that means these two triangles are going to be similar, and that means that the ratio of a to b here in this triangle is going to be the same as the ratio of x to y in this triangle. So that means any triangle that is right and that has this angle theta will have the same ratio of the opposite side to the adjacent side. So that means that we can really define something for this, right? Because every triangle has different side length, but the ratios are exactly fixed. So we should be able to define something that says, here's the fixed ratio for a specific angle theta. And here, what I just written in trig, this quantity is defined as the tangent of theta. And I just explained why we can do this. So it says that for any right triangle, if we know this angle, then we know the ratio of the opposite to the adjacent. It doesn't matter how big the triangle is or how small the triangle is, it's always going to have the same ratio. And this is why we can define this quantity called the tangent of theta. If the ratio changed between different triangles, then it would be absurd to define this because it would change based on different triangles. So the whole notion that we can define trig is because by fixing an angle, we get a triangle up to similarity, and the ratio becomes fixed, and we can define a specific, exact, unambiguous quantity for it. So this is just one example of a quantity. What are other quantities that we can define? Well, all ratios can be essentially defined in this triangle. So let's see what those are. So we actually have three sides in this triangle. So that means how many different ratios can we take between them? Well, actually, it's going to be 3 choose 2, or 6. It means we can do like the ratio of C to B, the ratio of C to A, the ratio of B to A, the ratio of A to C, the ratio of A to B, the ratio of B to C, and so on. So all 6 of them. And in trig, they define a specific, or they give a specific name to each one of these ratios. So I'll just go through these one by one. And these are just definitions. It's nothing complicated. It's just saying, because we know the triangle up to similarity, let's give names to each of these ratios. So the first thing that you'll see most often is called sine, or the sine of theta, which is going to be defined to be the opposite over the hypotenuse. So this is sine of theta, and it says whatever angle you have, look at the opposite side, get its side length, look at the hypotenuse, divide it, and get this ratio. And remember, because it's similar, any triangle, regardless of the side length with this angle, should have the same value of opposite over hypotenuse. So that's what we define to be sine. Similarly, we get something called cosine, which is just the ratio of the adjacent side to the hypotenuse. This is called cosine. So we just write that down. So after sine and cosine, we also have tangent. And tangent is the ratio of the opposite to the adjacent. So in this diagram, it's going to be A divided by B. Okay, so now we have 3 ratios out of the way, and remember I said there's 6, because the opposite of these ratios, C divided by A, C divided by B, B divided by A, are also things to consider. So the next thing that we can define as a trig function is something called secant of theta. And secant is defined to be the hypotenuse divided by the adjacent. So in this diagram it's going to be C divided by B. And then there's going to be cosecant, of theta, which means that instead of the adjacent divided by the hypotenuse, it's going to be the opposite, or instead of the hypotenuse divided by the adjacent, it's going to be the hypotenuse divided by the opposite. So cosecant of theta is going to be c divided by a. And then the last one is called cotangent of theta. And cotangent of theta is defined as the adjacent to the opposite. So the ratio of the adjacent side length to the opposite side length, and in this case it's b divided by a. So those are just a whole bunch of definitions, and we learned nothing new, but as I said, because this giving a specific value to this angle determines a triangle fully up to similarity, we can give specific names to each of these ratios, and and so then in mathematical expressions we don't have to say things like a over c, a over c, a over c. We can just say sine of theta, and instead of saying b over c and b over c, b over c so many times, we can just say it's cosine of theta. That's all that these things mean. So now the thing is, in a lot of trig, you'll see sine, cosine, and tangent a lot, but you won't see secant, cosecant, and cotangent as much. And why is that? Well, because sine of theta is going to be equal to a over c, but a over c is exactly the same thing as the reciprocal of c over a, right? If you flip it around, so 1 over c over a is a over c, and c over a is secant of theta, so that means that sine of theta is equal to 1 over secant of theta. So this means that sine and secant are almost related, and they're just reciprocals of each other. And similarly, cosecant is going to be the reciprocal okay, actually I got this wrong. So c over a is actually the cosecant, so be careful with that. So sine of theta is going to be equal to 1 over the cosecant of theta. So that means that sine and cosecant are related by reciprocals. Similarly, cosine and secant are going to be related by reciprocals, and tangent and cotangent are going to be related by reciprocals. So this means that using secant, cosecant, and cotangent in mathematical expressions are sometimes redundant and make them more convoluted than necessary. So a lot of times we don't really need these types of things in the formula. Now, what are other things that we can actually do with these expressions? Well, one thing is we know this thing called the Pythagorean theorem, which says that a squared plus b squared equals c squared in this right triangle. Now, one thing we can do is we can say, well, why don't we just divide out by c squared and everything, right? So we divide it out, and it will give us a divided by a squared divided by c squared plus b squared divided by c squared is going to be equal to c squared divided by c squared, which is going to be 1. Now, a squared divided by c squared is also the same thing as just a divided by c, quantity squared, plus b divided by c, quantity squared, is equal to 1. But we just defined here that a over c, or the opposite over hypotenuse, is sine of theta, right? So this is the same thing as sine of theta, quantity squared. And b over c we define as cosine of theta. So in this case, it should be cosine of theta squared, and that's going to be equal to 1. Of course, a lot of times we don't really want to say, sine theta parentheses squared, sine of theta parentheses squared. So mathematicians use a shortcut notation for functional notation, and they just write sine squared theta. So this is the same thing as this, they just have some kind of more convenient notation, and they have cosine squared theta, and that's going to be equal to 1. So this is just simplifying notation, so you can drop out the parentheses, and then you just move the 2 above the sign, and they're saying the same thing as that. So sine squared theta means what is sine of theta, and then square it. And so then we get the simple identity. So from the Pythagorean theorem, just doing some algebraic manipulation, we get exactly this formula, which says sine squared theta plus cosine squared theta is equal to 1. So really this is called a trig identity, but it's really saying nothing new aside from the Pythagorean theorem. But it's, it sort of gives us interesting ways of relating different functions together. And one of the other things to keep in mind is that sometimes trig expressions look complex, but there's a lot of redundancy in all of these expressions, which I'll show in a little bit. And so there's always relations between them, so sometimes even convoluted expressions can simplify to very simple things. So what is one example of that? Well, let's look at this expression that says that, how about cosine of theta divided by sine of theta times tangent of theta. Now what is this equal to? Okay, well, so even if we don't know any trig identities, what we can do is we can just directly plug in the definition. So draw a triangle, write out all these ratios, and just plug them into the equation, and just see what happens. So what is cosine of theta? Well, cosine of theta is b over c. Again, that's going to divide by the sine of theta. What's the sine of theta? That's going to be a over c. And what is the tangent of theta? Well, tangent of theta is going to be a over b. And now dividing by a fraction is the same thing as multiplying by the reciprocal. So this is the same thing as b over c times c over a, right? Flipping it around. And then this whole thing times a over b, the tangent of theta. And now what do? Well, now we can just cancel. So, the c's cancel because it's on a numerator and denominator. The a's cancel, and the b's cancel. So in the end, this whole complicated trig expression is the same thing as just saying 1. So, yeah, so it just means, plugging in definitions, there's a lot of redundancy, so even though these look like all different things, they really just say that this is 1. So a lot of times, when you see trig expressions, just plug in the definitions and try to simplify algebraically as much as possible, and you might get something very simple at the end. Now, one other thing I want to mention is that in a right triangle, there's two other angles that's not 90 degrees. So we labeled this one theta, but we can also label this one something else, like phi. Now, how are these related? Well, they're actually related very nicely. So one thing is, let's look at what the sine of phi is equal to, right? Well, sine of phi is the opposite side divided by the hypotenuse, but it's relative to phi. So that means the opposite side of phi is b. And the hypotenuse is c. So that means sine of phi is equal to b over c. Wait, but we've seen that before and it's here. So that's the same thing as cosine of theta. So that means if we just look at the other angle that's different from the one that we're considering in the right triangle, the sine of it is going to be equal to the sine of phi. It's going to be equal to the cosine of theta. What about, so this is just definitions. It's saying by definition, if we do this, then sine of phi is going to be cosine of theta. It's not saying anything new, just using definitions and relating them together. Similarly, for cosine of phi, it's going to be the adjacent side to phi, which is going to be a divided by the hypotenuse, which is still going to be c. So it's going to be a over c. And that was the same thing as sine, which we just defined. Well, then we can just say that it's sine of theta. Okay, so it's interesting, right? There's a dual relation between these two things and the two angles. And tangent of theta, similarly, tangent of phi is going to be equal to the cotangent of theta and so on. Right, so I won't go into too many details of that. But now, phi, so we have these expressions, but we also know that theta plus phi plus 90 degrees is equal to 180 degrees. So really, we also, if we just simplify this algebraically, we move 90 degrees, it says theta plus phi is equal to 90 degrees, and we will get that theta is going to be 90 degrees minus phi. So this actually, or we can also write the other expression which says that phi is 90 degrees minus theta, right? These are sort of complementary angles. So if we just substitute this in, then it would say that, the sine of 90 degrees minus theta is going to be the cosine of theta, and the cosine of 90 degrees minus theta is going to be sine of theta. So it shows that, so to just introduce some notation later, it would be that, sine is related to cosine by a phase shift, essentially.